Hi, everybody. Thank you so much for coming. And thank you, ChainStack, for hosting us. My name is Wei Jie. Today's presentation, my slides are very simple. I'm basically from geometry. We invest in deep tech, ZK startups at early stage. But I'm not going to talk about that. I'm going to talk about just one particular topic that I've been doing some research in. And this is called private information retrieval. And all the stuff I'm going to show you, I've learned from standing on the shoulders of giants. So it's like all this stuff is from a paper that came out last year called SimplePIR. And there's some references in the last slide, but I just want to go through how it works and explain what this whole thing is. So the whole idea is that currently when you go onto web services and you retrieve information from databases, most often the service that provides you the data, they can track your request and they track your IP. So if it's like a block explorer, they can see you want to know what's the balance of this certain address, and then they know your IP. And this can be said for many other things, like, for example, WebMD, which is like a medical encyclopedia. You search for sensitive medical conditions, then they know that your IP search for this condition, or even things like Wikipedia or any other database. So this is a pretty widely known issue, that there is you could leak private information from a third-party service. So what's the ideal solution instead of having that paradigm where you lose your privacy every time you ask for some data from some service? What if you could have a system such that you could ask for a certain piece of data, but the server has no idea which piece of data you asked for, but when you retrieve the answer from the server, you can decode it and get back exactly what you had asked for, even though the server has no idea what you had asked for. So for example, the user would send some kind of encoded request or query to the server. The server would do some kind of computation without knowing exactly which address they had asked about, and then they'll send back some encoded reply, and then the user would decode that and find out, okay, this address, which the server has no idea about, has certain balance. Okay, so what are the use cases for this? It's limited by practicality, because such schemes historically have been pretty slow, and only in recent years have advancements in the research made it such that they can be much faster, but there's still a lot of research and engineering to go into making these practical. So very simple stuff like block explorers, private contact lookups, private Wikipedia, private WebMD, and things like that. Just to make this relevant to the blockchain, Web3, ZK space, yes, there are applications, very niche applications to ZK, to Web3, and these have to do with retrieving proof data from untrusted third-party services that can do a lot of work for the user, so the user doesn't have to do all that work by themselves, but they still want to maintain privacy about what they're doing. Also a very niche, but that's more niche than we have time for today. So let's go into the actual building blocks of how this whole thing works. And I promise you it's really, really simple, because the protocol itself is called SimplePIR, and it's actually really simple. Anybody remember high school math? Matrix multiplication? Okay, I promise you that is the hardest part. And for me, this is the most complicated slide, because this is the most confusing piece of the presentation, how do you do the multiplication? So 1 times 1 plus 2 times 0 plus 3 times 1 is 4, right? So let's go through that again. You take the row and the column, and then you add and multiply and add, and you get the result. So far, okay? Okay. What's that? Yes, that's right. And the order is also important, yeah. And the number of rows and columns is also important. So it's like 3 times 2 times 2 times 3 equals 2 times 2. Okay. I keep getting this wrong. So last night I did the same presentation, I found there was a mistake because I got this whole thing messed up. Okay, so that's the first building block, and everything else is built on top of that. So the next building block is called regraph encryption, and this is based on the idea that, okay, let's say you have two matrices, A and S, you multiply them, you get B. If you don't know S, you know A and B, you can recover S.
I guess only if A is not all zeros or something.
So what's that?
If A is all zeros, you couldn't do it.
If A is all zeros, you could.
If you know B and you know A, but A is all zeros, then you can't recover S.
Yeah, but let's just say that A is not all zeros. Yeah. But you could.
It has to be invertible.
Yeah, it has to be invertible, yeah. But if you add some noise into the mix, if you add you do A times S plus a small E, then it's really hard. That's the underlying principle behind this thing called learning with errors assumption, which underlies regraph encryption. I can't explain like the actual proof behind this, but we're just going to do this step by step. And by the way, just to make sure that everyone is on the same page, all these numbers are going to be modulo some Q value. So if it's like modulo 7, 6 times 2 equals 12 modulo 7, which is 5, right? So it's like clock arithmetic, right? You're gonna do modulo that number. Okay. Okay, so I'm gonna go into some of the equations behind how to do encryption and decryption using the system. So the plain text, which is the thing you want to encrypt, is modulo P, and then everything else modulo Q. So for example, if you're going to encrypt plain text, which are bits, we can just say that P equals 2, because it's either 1 or 0. And then Q, in the example later on, we're going to use the number 7, because it's easy. A is some matrix that everybody knows, both the server and user knows. S is a secret key. C is a ciphertext that we get, and this symbol is like you take this number in between and round it down. So when we do encryption, we are taking the plain text, which is how do I get the mouse? Yeah, we take the plain text, and we multiply it by that value rounded down. And remember that we did this A times S plus E, and we add that. And the reason that this
Can you go back? What was P?
P is the plain text modulus. So all the plain text.
Oh, you just pick one. Is the P public?
P is public, yeah.
Okay.
P and Q, P, Q, A, everything except S is public. Yeah.
The plain text also not public.
What's that?
The plain text also is public.
Plain text is only known to the user. Yeah. So if the ciphertext equals that, and we want to get back the plain text, we're going to just minus off A times S. And because E is very small, E is basically less than half of Q divided by P rounded down. So when we round it to the nearest multiple of Q divided by P rounded down, the E is going to disappear by itself because we round it down. And then that's why you can get the plain text. I'm going to do like a step-by-step example, okay? But for now, there's two more slides about why this is interesting, and there's homomorphic addition and multiplication. So if you have two ciphertexts and you add the ciphertext together, it's the encryption of the plain text added together, as long as the secret is the same. So S is the same, but you can add two ciphertexts without knowing what's underneath it, and the encryption of that is the plain text added together. And also do take note that the noise vector E also gets added together. So if you add too many of them, it's going to overflow above Q divided by P, run it down, and then you're not going to be able to decrypt. But in our use case, that's not going to happen. We're not going to do that so much. And also, we must also add matrix A, so A plus A, and use the A plus A to decrypt later. Very similar with multiplication, but this time we are multiplying the ciphertext with the plain text to get the plain text times the plain text. And we also multiply matrix A by the plain text. Okay, so how do we combine matrix multiplication and regraph encryption to get this interesting but very simple protocol? Here is the intuition behind all this. It's like, if you don't remember anything, just remember this technique, right? You have some like 3, 4, 5, 6 database, and then you have this 1 and 0. You can multiply, if you do this, you get the first column. If it's 0, 1, you get the second column. You see the pattern? It's like super simple, right? Anybody want to do the math? Like just so 0 times 3 plus 1 times 4 is 4. 0 times 5 plus 6 times 1 is 6. So 4, 6, right? And then the other one, 1 times 3 plus 0 times 4, 3. 1 times 5, 0 times 6, 5. Okay. What happens if you do this? Anybody want to give an answer? Encrypted 5, 3, 5. Yeah. But that's right, exactly. Because of homomorphic multiplication, you get this result. So far, so good. Anybody want to ask questions? Feel free to just to ask, because anytime you can just ask questions. Okay. So here is why we are so interested in these properties of matrix multiplication and regraph encryption. If you have a database and you have a query, you can take the query, which is encrypted ones and zeros, or basically a bunch of zeros and only one of them is encrypted 1. You do the multiplication and you get the encryption of the row that you want. I mean, the column that you want. And from that, you can have private information retrieval. So how do you do that? Just take note that earlier I mentioned that you also have to multiply the public A matrix. So we can do that beforehand, send it to the client, and that's the bulk of the computation. The user will have to encrypt some like ones and zeros. Let's call it the query column, and the server gives the answer. And now, because the server doesn't know which of these values is 1 and which of these values is a 0, like they are not going to be able to tell which piece of data the user wanted.
All the encrypted zeros were different?
It's all different because they're using different S. Yeah.
Wait, different S?
Different secret vector.
So does this kind of imply that the user is aware of the way the data is arranged?
Yeah, we're gonna have to set like the parameters, right, so they know that the database is like n times n matrix. Yeah.
Is this encryption deterministic or is
It is deterministic.
So the user would have to use different S for every encryption of 1 and 0, and then has to track which one which was which and keep all the keys. Like we have 1,000 zeros in the database.
Yeah.
Keep track of 1,000 keys.
Yes.
At what point the randomness overflows into the information?
The noise vector. Yeah. So the limit. So noise vector should be less than half of Q divided by P rounded down, or even less than that actually. So depends on, okay, I'm not sure exactly the numbers because you must choose those values using a certain process. But once it exceeds half Q divided by P, then it overflows. Then when you try to round down, it doesn't round down because it's above half. So, because in this case we are not multiplying by much, we don't encounter the issue. Yeah.
You just asked if it's deterministic. You said yes, it's deterministic.
Yeah.
So if you have the same, if you make the same query twice, can the server learn that you query the same thing twice?
You'll make the same query twice.
Yeah.
The server still doesn't know which.
The server knew that you queried for the same thing twice.
Okay, then then it knows that you queried for the same thing twice, but doesn't know what the thing was.
Yes.
But you could also re-encrypt your query. You can just select different secrets and then send a new query.
Yeah, okay. So you would want to do that like this?
What's that?
I guess you would want to do that.
Yeah, I think so. Yeah.
Don't we choose the noise per encryption?
What's that?
Do we choose noise per encryption? Or
You do.
doesn't it take non-deterministic?
If you have, as long as the noise is below that limit, then it's fine.
Oh, no, I think you mean, so the whole protocol, once you fix the noise, is deterministic? So, but my answer was for Retrieval encryption was that you pick noise per encryption every time you pick new noise. Or you don't. Noise, you do.
You pick the noise. Yeah, you do. When you encrypt, you have to pick the noise. Yeah.
And so then every encryption with different, if I encrypt one with the same secret as, but noise one and noise two, the encryptions will be different.
Yes.
So then it's non-resistant.
Okay, I see what you're saying. But as long as it's in that sense, it is non-deterministic. But I understand it as it's just adding. As long as the noise is there's no the randomness it's just that. Right.
So we can reuse the same secret for the whole query. And just use different noise.
That's a good question. I'm not sure about the security property of that. Yeah, I'm not super sure. Maybe yes, maybe no. I need to. It's quite beyond the scope of the talk. But that's an interesting question, like whether you can choose different noise.
I think you can.
Okay, gotcha. That would be very helpful because that would have performance implications. Yeah.
In terms of the size of data being returned, is it zero perhaps?
Yeah, I'll show you some statistics at the end of the talk. Yeah. Rama, how much time do we have? Okay. Okay, so let's do a simple example by hand. Everybody ready for some math? I got this wrong last night, and then I had to fix my slides because I keep messing up matrix multiplication.
That's your computer.
And but I put in like the wrong numbers. So anyone want to? Let's skip this. Let's assume this is right because I'm sure it is. Okay. So we calculate the hint by multiplying the database and the public matrix A. When
Is the hint normally smaller than the database?
yeah.
Okay, because in this example,
It's smaller. Yeah. This is just a very simple example. Yeah. So this happens at the start of the protocol. When the user makes a query, they are basically, so let's say the user wants column 1, row 1, and we start from 0. So they want the second column and the second row. So we encrypt 0, 1. So that's like 1, 3 plus 1, 1 equals 2, 3. 1, 3 plus 1, 1. 2, 3. No. Did I get it right?
I think it was okay.
Wait, did I get this wrong?
No, I think it's right.
1,
So A times S in the first column is like 1,
3.
and then you're adding the error for 1, then you're adding a 0, and then you get 2 at the end. That's usually right.
1, 3, 2, 4,
Yeah, and then you get
2, 7, which is 2, 0. Okay. Okay. I got a bit of a panic attack like that. It's like, okay.
You should have put some arrows in so we
That's a good point. I should make that animation. So the query is 2, 0. I take the query and multiply it by the database, and then we get 2, 2. We decrypt the answer. We only decrypt the row that we want. And then we get that number and round it to the nearest multiple of 3, and then divide by 3. So it's 0 divided by 3 is 0. And the database is indeed 0 at that second column and second row. So we've just combine matrix multiplication, regraph encryption, and that very simple intuition behind how to do this scheme. And that's what we call SimplePIR. The authors of SimplePIR have also come up with double PIR, which is basically using SimplePIR on top of the hint so that you do it twice. The benefit of that is that, for example, with SimplePIR on a 1 GB database, the initial hint is 121 megabytes, but each query is quite small, 242 KB. They tested it on AWS, and they got some statistics about, some benchmarks about how much data they can process per second. If you do double PIR, then your hint is smaller, but each query is a little bit larger, and it's a bit slower on the server side. That said, all this is still quite academic. Like, I don't think there's very well-known like public implementations that are very practical today, and I think that's a very interesting area of like research and engineering that would be very interesting to see. Yeah.
Let's say we have to trust the server.
You have to trust the server to give you back a certain answer, but that the server will not know what you had asked about.
Oh yeah, but the server could lie to you.
The server could lie to you, yeah. Yeah. What's that?
It's in PIR doesn't add that.
Yeah, yeah.
Oh yeah. But it doesn't. Yeah, it doesn't add that. Just want to that doesn't give you any extra. You have to trust that the server gives you the right answer.
Yeah.
Do you know if they tried to do a triple PIR?
The paper said that, the paper tried that, but the paper found that after double, it's not really, there's not much of a point.
So the savings on the bandwidth?
In terms of savings,
Because we went from 121 megabytes to 16 megabytes.
Yeah.
Which is 8 times.
Yeah. I'm not sure. Yeah, but the authors said that like it reached a point where it didn't really make sense to do triple.
If you do like recursive queries, would that also increase your error chance?
Yeah,
I don't think so because it's two different errors, I think.
it's different, two different errors. Yeah,
Different combinations.
because yeah, the ciphertext there are two ciphertexts in double PIR. So I think it's a different error term. So there's some resources online. The paper itself, there's a very interesting blog post by the folks behind a startup called Bliss that does PIR as a service. And there's some sample, this is the link to the slides, but if you go to that repo in GitHub, you can find the Rust implementation that of SimplePIR and double PIR. Yeah, but still very experimental. I would love to see more like production stuff, and I personally like to like jump into that if, yeah. Any last questions before I hand it off?
Oh, so double PIR is just like increasing the dimensions of the database? Should I pay attention?
Oh no, double PIR is applying SimplePIR to the hint,
To the hint.
right? So now you have two hints, one hint for the hint and a hint for the database. Yeah.
Instead of transferring the original hint, you treat it as if it's in a database. Because computing the hint is the same as looking at
Get
the
like a row and then you guard it and then
I think so. Yeah, it's recursive application.
Yeah, also your second query won't just be a single row. It will be
It's tricky to visualize. Yeah, but but I think the paper has a much clearer like step-by-step algorithm, and the code does show that. Yeah. This is basically all regurgitating from the paper. So just want to present something that seems very interesting and has potential for the future. So yeah. Thank you.